you'll be interested in listening to me for just a few minutes, I'll try and make it quick and get to our featured speaker. I'm Marion Weiler. I'm the program director for the San Mateo County Astronomical Society, your host for tonight, or co-host, because actually this is being co-hosted by KIPAC, the Kavli Institute for Astrophysics and Particle Cosmology, or something like that. That's close enough. Okay, and I know we have a lot of members from there, and we want to welcome you. It's awesome to have you here. I also want to do a great shout out to Michael Gallion, who's the CSM planetarium technician back there, the jack of all trades that keeps this place going. We are guests here, and we very much appreciate CSM and Michael's kind of efforts to host us here. And so give them a round of applause, please. Great. Okay, without further ado, I want to introduce tonight's speaker, who's standing patiently next to me. Theo Schutt is a 6-year PhD student at Stanford University and SLAC National Accelerator Lab. And he's a member of the KIPAC, which I don't have to go through that again. Thank you. Theo is an observational cosmologist specializing in weak gravitational lensing, the study of how light from very distant galaxies get deflected by foreground clumps of matter. Theo's work focuses on analyzing data from the Dark Energy Survey, mapping the lensing of nearly 150 million galaxies to better understand dark energy, which is the mysterious force driving the accelerated expansion of our universe. It's going to be interesting. Okay, Theo is also involved in the Vera C. Rubin Observatory, having contributed to the characterization and commissioning of the main instrument, the LSST Camera, at SLAC and also down in Chile. I believe we're going to hear about that. I'm sorry I didn't realize you may not have heard me because I was holding the mic up properly. But anyway, I'm done. With that, let's welcome our speaker. And Theo,
Yeah, thank you for that very kind introduction, Marion. And thank you all for coming here. I'm super excited to be able to share my experience working on this incredible observatory. So before I begin talking about Rubin, I just wanted to give a brief personal introduction. So I'm originally from Colorado, and so I grew up in kind of the middle of nowhere. So I had lots of access to beautiful skies and beautiful night skies. Though actually I can't say that I really wanted to grow up and become an astronomer. Most of my childhood I actually wanted to be a marine biologist, despite never seeing the ocean until I was like 18. So that's why I've arrived here. And yes, so very happy to share this work with you. So before I begin, I actually wanted to get a bit of a read on the room of how many of you have heard of the Vera C. Rubin Observatory. Okay, wow, great. Yes, so as many of you know, this observatory is named after Vera C. Rubin. And she was a pioneering astronomer in the 20th and 21st century. And she is basically considered like the mother of dark matter. So she studied the rotational motion of stars in other galaxies. And so this is kind of one of her key results from her career. So this is looking at our closest galaxy, M31, or the Andromeda Galaxy. And what she really studied was looking at how looking at how fast stars rotate around the center of the galaxy. And so that's what this curve here is, and the data is basically showing the speed of stars rotating as a function, depending on how far they are from the center. And so if you if you just looked at the stars that are in the galaxy, you'd really expect this to go quite far down. But instead, we actually observed that they keep going quite fast, even quite far out in the galaxy's reaches. And so the main result that Vera Rubin and her collaborators surmised is that there must be a lot more matter way out here that we cannot see. And so that is the kind of main result of this work, is really the first strong evidence of dark matter, which is, we now know, makes up about 85% of the matter in our universe. And so the Rubin Observatory, before we once it was at its very beginning, is actually called the Dark Matter Telescope. So Vera Rubin is really quite a fitting namesake for our observatory. Okay, so from here, I'm going to take you on a journey to Chile and to Rubin. And so let's get started. Yes, okay. So if we want to go to Rubin, we have to go down to Chile. And so the way we get there is by flights, several flights. And so we go from San Mateo here down to Chile here. And it says it's 16 hours, but it's more like 24 hours, so it's quite a journey. But once we get there, we're at the beautiful La Serena, Chile, which is our base camp. So not too difficult to live there. And so this is kind of where the base operations for Rubin are. It's in this beautiful city on the beach. But if we want to go to Rubin itself, that's a 2-hour drive. So we go from La Serena, and then 2-hour drive through the mountains up into these are the foothills of the Andes Mountains. And so this 2-hour drive, kind of the end part of it is a bit harrowing. So this is a picture going up the mountain, and there's a pretty steep cliff drop on the side there. But there's some really beautiful views as you go along the road. So this is, we're approaching the ridge where 3 telescopes are. And you also get to see horses and other wonderful wildlife. So people kind of call it a desert, but there's actually quite a bit of wildlife around the Rubin Observatory, so quite fun to see. And then once you get quite close to the observatories, you get to see this ridge with 3 observatories. The SOAR Observatory, which was built in the 80s, Gemini South, which was built in the late 90s, early 2000s, and then Rubin Observatory here. So they look a little small from a distance, but as you'll see, this is quite a large observatory. So this ridge is called Cerro Patron. It's very close to a couple other ridges with other observatories, but this is my favorite one, Rubin Observatory. And so I'm going to kind of give you an overview of the science that we get to do with this wonderful observatory, and kind of why we've built it in the first place. And then I'll kind of go into more detail of what's inside the dome and what I've been working on as well. So this observatory is a survey telescope. So most observatories that are in the world, you kind of have a smaller field of view, and so you pick targets to take images of. And so you know what you want to look at ahead of time. On the other hand, Rubin works as a survey telescope, so it's actually tiling the entire sky. And in that way, it's really going to be kind of a discovery machine, where we're looking everywhere and we really don't know what's going to pop up. And so we'll be imaging the entire southern night sky every 3 to 4 days. And we will do that for 10 years. And so over 10 years, each patch of the sky will have about 800 images, and that will be over 6 different filters. So we'll have 6 different colors of images. And so what this ends up being is really a 10-year movie of the entire night sky. And so we'll both have like a very broad view, a very deep view. So we'll see things that are very faint and very distant, and we'll get to see them as they change over time. A lot of the images that we take of any one spot, we come back to multiple times a night, and so you can see things that change within a night and over the full 10 years. So there's lots of science goals that would benefit from this survey strategy. And so I'm going to go over kind of the five main topics that people are interested in for Rubin. So the first is the solar system. We'll be cataloging pretty much every object in our solar system down to 100 meters. And so this will be incredible for asteroids, comets, etc. And then kind of stepping out, we'll also be watching our own Milky Way. That's over here. And so we'll be surveying more stars than ever before, about over 17 billion stars. And that will be especially important on the edges of the Milky Way where they're quite faint. So we'll be able to discover kind of our neighboring satellite galaxies or dwarf galaxies. As I mentioned, we also see how things change over the night. And so that's really important for this looking at the changing sky. So every night we will be producing about 1 to 10 million alerts. So that's anytime we see a star change brightness or a galaxy change brightness, etc., or see, for example, an asteroid moving, we will note that and then share it to the public within about 2 or 3 minutes after our image is taken. And so we do that about 10 million times a night. So it's pretty dang cool. Sorry. Okay, and then from here, we also do kind of much larger scale science. So that's mapping dark matter with galaxies. So as I said, it makes up about 85% of matter, but the galaxies are the only thing that we can see. And so we use those as a proxy. And then finally, we also want to measure dark energy. So this is as Marion mentioned, it's the mysterious source of the accelerated expansion of our universe. And so we'll be combining many different observations to try to measure this over the whole history, or very far back history of the universe. And I just wanted to point out which of these topics that KIPAC is quite interested in. So we're kind of mostly involved in these 4 on the right. These are kind of the particle astrophysics and cosmology topics. And then the kind of research that I do, as Marion mentioned, is in this weak gravitational lensing. And so the main goal of the science that I do is looking into basically the how dark energy works. Okay, so from here, I want to kind of, now that you know like why we want to do this science, we can now I'll show you some of the beautiful images that come from Rubin and what information we can take from them. And so earlier in 2025, Rubin released its first images to the public. So I'm actually curious now, how many of you know about this, what was Rubin's first look images? Okay, yes. Okay, fewer than, okay. So that's great. So I'll show you one of these images. And so this is the Trifid and Lagoon nebulas. The Trifid is the top one, kind of bluish one. And these really show Rubin's power, because there's really no other observatory that does what Rubin does in combination. So Rubin sees a wide space. It goes very deep, and it does this quite quickly. And so lots of other telescopes do maybe 1 or 2 of those, but Rubin really does all 3 very well. So, so this image, I wanted to show kind of what does Rubin see in one image. And so that's this circle here. It actually goes off the image a bit. So that's what what Rubin would see in a single image. And then you can compare it to something that maybe more people are familiar with, like the Hubble telescope. And so that is about that size. So much, much larger. And so it actually turns out that one Rubin image is about 4,000 Hubble images in area. And so that's really kind of what's groundbreaking about Rubin, is how fast we will be able to cover the night sky. There's really no other telescope that does it like we do. And so, yes, so the next image that was released is this beautiful extragalactic field. So this is called the Virgo cluster. So this image, which isn't working quite well. Okay, there we go. So, so now I'm showing the same circle as before, what Rubin sees in one image. And so you can see that as opposed to what we were looking at before, which is in our own galaxy, when we look off into areas that are completely blank to the eye, this is what pops up. And so in this image, there's about 10 million galaxies, and this is only a fraction of a percent of the whole sky that we will be looking at. And so I wanted to just give a quick zoom in on one of my favorite parts of this image, because it's just so beautiful. So we'll be zooming in on this little square here. And so we get to see this beautiful merging system where we have galaxies interacting with each other gravitationally, stripping stars away from each other, etc. And so this really shows that we'll be able to get even these very faint features that we see at the edges of these galaxies, which are quite hard to capture with other observatories. And we'll be able to see this kind of detail across the sky. So, and then I just wanted to point out that you can actually see these images online. So if you check out skyviewer.app, particularly this whole field, you can see in full resolution. And it still blows my mind, actually, when I bring it up, how huge this field really is. Okay. So from here, now that you've gotten a bit of an intro to the data, I wanted to give you a tour of the facility itself. And so we will now take a tour of Rubin Observatory. So as Marion mentioned, I spent time down in Chile this past year. So I spent 3 months there as we've been getting the observatory working. And so I wanted to kind of give an overview of the observatory itself. And so, okay. So this is a video of what we have inside the dome. So this is going over what the telescope is made out of. So indeed, we have one main mirror that has 2 different types of curvature. And so it acts as both the first mirror that the light sees and the third mirror. And then we also have this secondary mirror up top. And so as you saw, light kind of comes in on the first, hits the second, hits the third, and then goes into our camera.
A little louder.
Okay, sorry. Yeah. And so the point of the 3-mirror design, so it's actually not very common for a lot of professional telescopes to have 3 mirrors. But really the point of it is to keep the telescope as squat as possible, as compact as possible, because we need to move as fast as possible. And so that really is what drives the design of this entire facility, is being able to cover the entire night sky very quickly. And so now that you've seen kind of an animation, we can look at real photos. So this is a photo of the telescope. And so indeed you can see what we saw in that animation. There's that's the primary and tertiary mirror. There's LSST camera itself, and then above it but hidden is the secondary mirror. And so for scale, the camera is about as wide as I am tall, so that might give a bit of a scale. But for a better look at the mirror itself, you can see in this picture here, this is the telescope facing horizon, or facing to the side. And so we see the mirror here, the primary mirror, and then there's a changing curvature here. So this is the tertiary mirror, or the third mirror. And there's really no other telescope in the world that has this kind of such a large combined glass mirror. And let's see. And so, so this even I feel doesn't give a very good sense of scale. So here's a couple other photos. So you can see my colleague Ilona Erbach here, next to the telescope here that the New York Times took. And then there's also little me over here to give a bit of a sense of scale. So that's the back of the telescope that's holding up the mirror. Okay, and so from here I want to go into kind of what many call the crown jewel of the Rubin Observatory, which is the LSST Camera. And as I think many of you know, the LSST Camera was built here in the Bay Area at SLAC National Lab. And so I'm kind of curious, like, how many of you have visited SLAC when the camera was here? Okay, nice. Yes, so yes, it used to be part of the public tours at SLAC until we shipped it away to Chile in 2024. And so here it is on the telescope. So now this is basically the telescope is pointed to the side, and so the camera is right here. And then these two people are Stuart Marshall, who's a SLAC staff scientist, and Yosuke Utsumi, who used to be a SLAC staff scientist and is now a professor in Japan. And these two are really my main mentors as I was working in Chile. And we have much to thank them for getting the camera running and well maintained. And so from here, you can look at the focal plane. And so this is looking into the camera through 3 lenses, and then you can see the array of sensors. So there's 189 science sensors, and so and you might notice that they have 2 different colors. So that's just because there's 2 different companies that made the sensors, and so. Yeah, so they didn't talk to each other when they were making the anti-reflective coating, and so they had quite different formulas for their anti-reflective coating, so that's what you see. But thankfully we can calibrate that out, so it's no problem. And so, yes, so I just wanted to go over some of the very cool things about the camera. It's the largest digital camera in the world. We have the Guinness Book of World Records to prove it. Indeed, it's about as big as a small car, but weighs quite a lot more. It's about 3 tons. Any one image is made up of 3.2 billion pixels. And so if you wanted to show one Rubin image at full resolution on 4K TVs, then that would take 380 TVs. And so I think one of my colleagues has shown that that's about a tennis court size of TVs. And then further, the sensors here, in order to have the cleanest images possible, are cooled to about -100 C, and I forget how much that is in Fahrenheit, but it's quite cold, about 100 50, I think. And so yes, so there's really no other camera that is as advanced as this one of its kind. And that's so that we can do the science that we need to do with Rubin. To be able to go as deep as possible, we need it to be cold. To go as wide as possible, we need it to be big. And so every single piece of design in the camera is towards getting the science that we want out of Rubin.
Minus 148 Fahrenheit.
Oh. Thank you. Okay, minus 148 Fahrenheit. Yes, pretty dang cold. Okay, so what have I worked on the camera? So I did work both at SLAC before we moved it, as well as work in Chile. So this is my work that I did at SLAC. So that's me in the clean room that was up at where the camera used to be. So what we see here is the camera facing down to the ground, and then there's this box that encloses the area where the focal plane or the sensors are. And so one of the big goals of our work at SLAC after building the camera was to make sure that we understand how it works. And so that's what we call characterizing the sensors. And so that was my main job, was to build a light source for characterizing the camera. It's actually the main light source for it. And so that's what this light here, it's you can see that it's pointing up into the camera, which is pointed down. And so this is kind of a zoom in. So this is the light. This is a zoom in of that light source. And so the point of it is to be able to shine uniform light over the sensors. And so we want to be able to basically see any defects or other issues with the camera and be able to then correct it. Light source would give us. So it's what we would call a flat field. So you just shine very uniform light, or at least very smooth light onto the sensors, and then see what pops out. And so you can see that, there's, for example, this sensor has some issues, as well as these are kind of stick out. And so we totally expect there to be these sensors not to be exactly the same, but we need to be able to do this kind of testing to be able to correct for it. And so that's what the point of this work is. And then further, we can do this in each color that we have for the filters. So the filters kind of cut out different wavelengths of light. And so we have different LEDs that cover each of those ranges. And so we took about 50,000 images with this light source to be able to get this kind of data over all of the sensors. And so this is really essential work for getting science out of Rubin. And so this is kind of we use it for different reasons. So sensor calibration, as I mentioned. So that's for experts in the room. This is a measurement of the gain of the sensors. So kind of how we convert photons, packets of light, into voltages that we can actually measure with electronics. And then this is some very fun turbulence that we found within the camera. So that you can see these features are actually turbulence from a fan that's blowing inside of the camera. But thankfully, we found that doesn't matter, so that was very good news. And then this is the last image is a zoom in of one sensor. And so this is looking at this very fun sensor defect that we call tree rings. And these really are basically tree rings because they come up as the sensor is grown from silicon. And so these effects are actually showing the different environment, how the environment changed as the sensor was growing. And so, as I say, there's lots of non-uniformities. No camera is perfect, but we have to take all this data to make sure that we can correct for those non-uniformities. Okay, so from here, I'm going to go over kind of what I was doing on the summit and what people do to get the actual data out of the observatory. And so this is kind of a look at the brain of the observatory, which is the control room. And so I took this at night, so you can see that a lot of the offices are empty. So these are the offices for the engineers and technicians and other support staff who've all gone home. But at night, the control room is quite busy. So you can see many of my colleagues here looking at the data as it comes through. So that's, we basically show every past image here. And then also some, lots of other information about the observatory. So this is my empty chair here. And so what we look at as the camera team is a lot of this monitoring info. So while the observatory is being commissioned or we're getting it running, we have to look a lot at this information about the camera. And so this is, for example, information about the system that cools the CCDs, because they are both cooled and kept at very low vacuum or high vacuum. And so we monitor those things. We also monitor, so the screen shows the observers basically when to close the dome to keep the camera safe. Because there are lots of environmental reasons why you'd want to keep the camera protected. And so that's what a lot of our work, so this is Yosuke here, a lot of our work is making sure that those are monitored and getting that information to the observers. And so next is the observers. So that's the two people over here are the observing specialists for Rubin. So there's a team of 16 people who who are on shifts. These are the people who are actually driving the telescope, watching the data come in, ensuring that it's the proper quality, ensuring that the data that we want to take is what's being taken. And so a lot of what I was doing in Chile was actually training the observing specialists on how to run the camera and how to monitor the camera. So this is a really key step to us moving from this kind of commissioning phase of getting things working to running the observatory, because there won't be us camera people up there anymore, and there will just be the observing specialists. So they need to know how to do our job. And so that was a lot of what I was working on while I was there. But there was also just a lot of us coming in and doing work both during the day and during the night. And so I'll remind you that when you're there in the summer up here, it's winter down there. So December is the dead of winter for Chile. And so that's kind of one of the most exciting days that we were there was when this snowstorm came in. So this is looking, standing right below the observatory, and you can't even see the dome anymore. And so this also meant that me and one other grad student, Sean McBride, had to actually camp out in the observatory. So this is very much not normal. There's a hotel that's about 10 minutes down the mountain where we usually stay. But we really wanted to make sure that the camera would be safe and that we'd be able to respond to any issues. So we volunteered to hang out in the observatory and make sure that the camera was well taken care of. And so we ended up camping out in the IT room, the warmest room in the building because it's right next to all the servers that are taking in the data. So now we know. Yeah, so we did this kind of, some suffering for the data, but I think it was very much worth it. So so there was some data that actually got taken very close to this time. Not when it was super cloudy, but a little bit before. And so that's some of the earliest science that has come out of Rubin has to do with this data that was taken. And so that was of this very interesting object, the 3I Atlas. And so this is an interstellar object, which means it's an object that came from outside of our solar system and is passing through. And so it's only the third ever interstellar object ever detected. You might remember Oumuamua, which was detected a few years ago and caused quite a lot of controversy about aliens or something. So this one we're pretty sure is not aliens. We're pretty sure it's just a comet, but very cool nonetheless. We really don't know about like what objects coming from different solar systems. We don't really know how they should compare with our own. So being able to study more and more of these objects over time is really important. And so this interstellar object was discovered by a different observatory, ATLAS, on July 1st last year, so 2025. But it turns out that Rubin had actually observed it quite a bit earlier, on June 21st. This happened to actually be the very first night that we were running like real survey data. So we happened to catch it in that night. And so we have figured out, once we heard about it from Atlas, we kind of went back into the data and tried to find it and see if it was there. So it was. And then we continued to have a few more observations of it that were just serendipitous. We weren't actually targeting it, but it happened to fall in our field of view. And so these are some of the images that Rubin has taken. So this is all on one night, and passing through our solar system. And then this bottom image is a co-added image. So basically, if you take every image that we've taken of 3I Atlas and stack them, so that you can see the faintest features of it, that's this bottom image. So you can see that there's a little tail. It's not quite symmetric, and so this is how we know that it's a comet. And so this is really a taste of what's to come. As I mentioned, we saw this totally serendipitously. We weren't targeting it at all. And so we expect to have tens, if not more of these every year. And so we'll go from, what we have right now is three discovered in the entire history of astronomy to probably hundreds just in a couple of years. And this the system that we have for delivering alerts to the public just started last week. So this was quite a momentous occasion that both professional astronomers are really banking on Rubin data, as well as plenty of amateur astronomers who are also super excited. So these alerts are public to literally everyone. And so that's actually part of what really draws me to Rubin Observatory, is being able to work on something that's so public. The data has pretty unprecedented access, particularly for US-based folk, but even people outside of the US. And then I wanted to mention actually that this discovery or observations of 3I Atlas we recently published. And so this is the author list for that paper. I'm in there somewhere. And so there's 300 authors on this. And it really shows that teamwork really does make science happen. This work couldn't have happened without the work of every single one of these people. And so that's also part of what I really love about working on Rubin, is being able to work with this very large team to get pretty incredible results out.
Would we all fit in one image on the telescope?
I'm not sure. I'm not sure. If we really squeezed in, maybe yes. Yes. So, so these are all professional astronomers and engineers and technicians. But I wanted to point out that there are also many opportunities for citizen science. And so, as I mentioned, Rubin data is quite open. So currently there's 2 projects on Zooniverse, which is this platform that connects professional astronomers with amateur astronomers. And so there are lots of projects that really could benefit from people becoming experts, like yourselves, learning how to do science with this data and helping reach new results. So that's these 2 projects are the ones running right now. So this is the Rubin difference detectives and the Rubin comet catchers. And so these are 2 projects to basically look at these changing images coming from Rubin and trying to figure out what's a real change and what's bogus, or what's a real comet, what's not. So that really benefits from just a lot of eyes on our data, especially as before we're doing work with, basically it helps to train the AI models that will be running on the full sets of data. And so it's very good to have the actual humans starting that to start. And so these are the 2 projects right now, but there are many more to come once we have more and more data. And so if you are interested at all in using Rubin data, there's a public forum, the Rubin Community Forum, and that's open to literally anyone. It's for general discussion and also community support. So Rubin has quite an extensive team that is paid to support the community, which includes professionals and amateur astronomers. And so this is a resource that I'd really suggest that you check out if you're interested. And also, in case these are not quite what you want to work on, but you have maybe another idea for the Rubin data, US-based amateur astronomers can actually petition to get full data right access. And so if that's also something that you're interested in, it's very, very much possible. Okay, and so from here, I just wanted to say kind of what is on the horizon for Rubin. So as I mentioned, there's some data out right now, but that was kind of preliminary data that was taken from not even like back in 2024. But the data that we're taking this past year, from June to this just past January, will be released in June. And so that's going to be a huge deal for many people in astronomy to be able to see this data over a very large field that's close to what the survey data will look like. And then there's the actual 10-year survey that the Rubin Observatory was built to do. So we've been saying that this is going to happen next month for probably about 5 months, but I really do think we're getting close. So stay tuned. And yes, so once the survey is starting, we'll be producing alerts, producing new data, and so there really will be absolutely groundbreaking science happening very, very quickly. And there will be many opportunities also to engage. So I recommend you check that out if you're interested. And you're also very much welcome to reach out to me, especially if I can help you connect to the Rubin data. That's something I'm very interested in. So yeah, so please feel free to reach out. And I can also share my information to one of the organizers. And then finally, I just wanted to say a huge thank you to both everyone that I worked with at Rubin. It was an absolutely fantastic experience, really, yeah. it was an absolutely incredible experience, kind of career-defining moment. And it's really great to work with all these people to build this incredible instrument. And I also wanted to thank all of you as the US public. This is obviously not possible without the support of science. And so I'd also like to thank you as well. And so, yeah, that's it. Thank you.
Live on the mic. Okay. Thank you so much, Theo. That was great. And I think at this point we're going to open up for general questions. And we have a special guest tonight that's going to moderate the questions. I'll introduce Xinnan from KIPAC.
All right, you guys can hear me well, right? Okay, wonderful. So we're just gonna have the Q&A. I think since we do not have another mic, I am also going to repeat the question. Yeah, and I see a hand over there. Oh, yeah, you're a gentleman, yeah.
What is the size of the photosites on these chips, and what is the foreground capacity in terms of electrons in the stored data?
Oh, okay, so the question is, what is the size, the physical size of the sensors, right? The CCD?
Individual pixels.
Yeah, the pixels. What's the size of each pixel, and what is the full capacity when it's collecting photons, right?
Collecting photons and storing electron charge.
Yeah, and just storing electron charges, if you have those numbers on.
I do. I have them off the top of my head. Yes, so these sensors are 4,000 pixels by 4,000 pixels. Each pixel is 10 microns. And then the full well capacity is about, it's a little bit less than 100,000 electrons. Yeah.
Well, very incredible.
Yeah,
You remember all those?
I know that.
All right, right here.
How much of the night sky does it scan in per night?
Okay, so the question is like how big of a sky it can scan per night?
Yes. Yeah, so we're covering the entire sky in like 3 to 4 days. So yeah, we're basically covering about a third of the sky in 1 day. But that's also accounting for the fact that we're repeating the same spot over and over and in different filters. So yeah, so that's.
Did you mean like a third of the entire like 360 degrees, or like the southern sky?
Yeah, that's the southern sky. Yeah. So we cover the whole southern sky in 3 to 4 days.
Yes.
What kind of AI models are you using? Are you using convolutional neural networks, you use transformers together, or what does that look like, the architecture of your models?
Okay, so another technical question. What kind of AI models are you using in your work? And specifically, you said, like you work on weak lensing, like dealing with the data, sharing a little bit about,
Yeah. Yes, so so the AI models that I was thinking of or talked about is more for the changing sky. So that's not something I'm super familiar with. But we do work also with AI models on both the observatory itself. So some of the basically checking if images are bad or not. That's done with AI, or one of the ways to do it is with AI. Although I'm not sure what the exact model is. And then for weak lensing, most of that is kind of we'll say traditional programming, but there are lots of new methods coming out, particularly for basically ways to handle this huge amount of sky area. And so a lot of those use basically like CNN's convolutional neural networks. And so that kind of embedded in a much larger pipeline is how we do some of the modeling.
Was that a satisfying answer?
Sure.
Okay, great. All right, I see another hand over there.
What energy source do you use to power the observatory?
Great question. Okay, so, yeah, you mentioned a lot of the, all the moving pieces, and especially the very warm server, right? So
Yeah.
there's got to be an energy source for the observatory. What is powering it?
Yes. Yeah, so that's a great question. we have actually many electricity sources. So the main source is just commercial power, like the Chilean national grid. And so I do not know what the full breakdown of the Chilean national grid, so not sure. But we also have lots of backups. So the grid, or like commercial power, we have outages semi-frequently. And so we have 3 backups. So there's 2 diesel generators, and then there's also a different diesel uninterrupted power source. Basically, it's the power source that lets our camera, for example, keep running even when there's like a short dip in electricity. But I will say that the organization that runs all of these US-based telescopes is really interested in converting a lot of our energy usage to solar. So on that ridge that I showed you, there are plans to build like quite a large solar panel array. So I think it would be able to power something like 20 to 30% of the energy, I think, for all 3 of those telescopes. Although don't quote me on that number. But so we're at least in the process of converting to more renewable resources.
Great, thank you. Okay, so I'm gonna move here so I can see better. All right, over there.
So if the telescope is so remote, then shouldn't there be some kind of like mini corner, like a living space?
Yeah, okay, so you mentioned that, on the mountains, especially with a 2-hour drive, right? It's a very remote location. So shouldn't there be like a living quarter for all the observing specialists or whoever is actually supporting the telescope on site?
Yeah, yes, that's a great question. So yes, so there is, so no one lives at the observatory itself, except that one time where we slept over. And that's very much not a normal situation. But rather there's actually a hotel. It's a tiny, like 20-room hotel that's built specifically for the observatories on this ridge. So it's shared between those 3 observatories. And it's about a 10-minute drive down the mountain. And so, yeah, so everyone is kind of there overnight. So indeed, like the observing specialists or the camera support team, we would usually sleep at the hotel, and we basically stay there for 3 to 4 days, and then shift off to someone else. I will say though, that a lot of the day staff, who are mostly Chileans, the engineers, technicians, support staff, actually make that 2-hour drive one way every single day, or every day that they're working. So we have like a chartered bus that takes all of us up and down, but they're pretty, very dedicated people working on the observatories.
Yeah, it's quite surprising to hear that, bad commutes are everywhere.
Yes.
Even in Chile. Yes. Yeah. All right, over there.
Yes, you said 3.2 billion pixels per frame. What type of database can store that much data for 10 years?
Yeah. So great question. So the question was, you mentioned that, like each image was incredibly high resolution, right? So like what is the facility or the power for us to store and also like to transmit that kind of data? And you also mentioned, public alerts are out like in 2 to 3 minutes. Like what's the process?
Yes, so that is an excellent question, and that is indeed probably one of the biggest technological needs of Rubin, is to figure out where does the data go. And so there's kind of a few different places it goes. So Rubin actually built its own fiber optics cable under the ocean to pipe the data to the US. And so it gets piped all the way to SLAC here in the Bay Area. And so there's what's called the US data facility. And so all the Rubin data gets saved there. And then it's a facility shared with other physics experiments at SLAC. But besides that, there's also some redundancies. So the data also gets saved in a data center in France and also in the UK. And so they're very much involved in the like processing and such. And so Rubin has quite a extensive data management team. I think it's fair to say probably the largest data management team of any observatory. So it's spread between both SLAC and Princeton and also these UK and France facilities. Yeah. And then there's also the servers themselves on the summit. And so the summit servers can hold, I think, 10-ish days. If, like, for example, if the internet went down, we would still be able to keep running the survey and just start, building up the backlog. So there's lots of redundancies everywhere.
Thank you, Theo.
Yeah.
I'll come to you next. Your friend.
So what is the limiting magnitude in a typical survey image? And if there should be perhaps a dim, interesting target of opportunity, is there any flexibility in the schedule to go to longer exposures in the imaging?
Yes, that's an excellent question. So for a single image, it's obviously depends on the filter. But for example, kind of in the middle of our range, the limiting magnitude of one exposure is about 24.5-ish. And then the depth for the full 10-year survey is something on the like 27 point something magnitude. Super deep. But it's wild to me. So yeah, because like one image, I think about one image from Rubin is about the depth of the dark energy survey, which is the other project I work on. So it's wild to me that, that they can take that much data that quickly. And then for targets of opportunity, so yes, so this is when we get some sort of information from a different observatory that there's something interesting that we would want to look at on the sky. So yes, so Rubin has a dedicated amount of time per year that we can use to target other like interesting phenomena. So in fact, the interstellar object I mentioned was our great test case for this. So that was the first time we did this target of opportunity testing. So yeah, so you basically have to like stop the survey as it's going, which is all automated. So you stop it and then start doing observations elsewhere. And then we also have done it for a gravitational wave event. So that's definitely the biggest portion of what Rubin will have time to do, is for when there's some sort of merger event that the gravitational wave detectors see. So this is like usually a black hole and black hole merger, or a black hole neutron star merger, or neutron star merger, like these types of things. Once that happens, if they have a small enough area on the sky, then we can follow up. And so Rubin is super good at this because we can cover so much of the sky so quickly. So I think we covered, for the gravitational wave event that we had a few months ago, I think we covered about 800 square degrees within a couple of nights, over 2 bands, I think. So pretty impressive. Yeah.
Yeah, and I think there's also a committee actually working on, selecting which of these targets to follow up on, and there are also like KIPAC people actually in that committee. So, yeah. Okay, over there.
I was wondering what was housed in it looks like about 3 to 4 story structure that's off to the side from the telescope, going down the hill.
Yes.
Oh, okay. Yeah. So the question is, Theo, do you want to show the picture? So, very observant. There's a few story structure just right next to the building.
Yes.
Do you want to comment on what it does and what it...
Yes. Okay. Yes. I was ready for this question.
Yeah,
So-
do you want to point out like where the structure is?
Yes, so what this person's talking about is this structure here. So it's a small observatory or a small telescope that's next to and works together with the Rubin Observatory. And so it's called the Auxiliary Telescope. And so,
No, I
Oh,
was
no.
referring to the structure that's.
The stair-step
the
buildings there.
stair-step building, thank you.
Oh,
Or-
okay, so,
Which one?
yeah, like almost like the end.
Patio.
of- Yeah, right here, yes, what's happening?
Okay. I was not expecting that question. Yes, okay, so this is a key part of the observatory itself. And so you can see there actually is a patio. It's right here. So that's our kitchen. That window is into our kitchen. That's right off of the control room. And so we in the control room sit right below a huge storage space, hangar type area. So, do I have a picture here? I don't think I do. So this is where we used to store the mirror. So the mirror is, over 25 feet large and then has a holding structure as well. So that was held there. The camera also, there's a small clean room in this area. It's basically right behind this hangar door here, where the camera was placed between when it got shipped there and when it got installed on the telescope. And there's also, importantly, a mirror coating chamber in this area. So I think Rubin can recoat the mirror on site instead of having to ship it all the way down back to Las Reina or elsewhere. And so, so that among other things is in that structure.
Since you were about to tell us, though, what was on?
Okay, yay! I love Oxtel, so I think it's cute. Okay, so Oxtel helps us calibrate our images. So I can show, yes. So it's a 1.2 meter telescope. And so we're in the dome looking at Rubin. And so this has a spectrograph on it. And so we use it to observe kind of standard stars in the sky and measure the atmospheric, the extinction. Yeah. And so we're able to kind of get an external constraint on the extinction wherever we're looking. So it provides us kind of this extra information to do calibration.
Great. I know we're almost running out of time, but officially with the Q&A, but Theo will still be here, and even after our event ends, you guys are more than welcome to talk one-on-one with them. I know we have a hard cut out just to close the planetarium. So Theo, maybe you can help me show. So just a quick plug. This is actually our first lecture in the Rubin Engagement Series, and it's wonderful also to see many of you as regular attendees of KIPAC events here. So the next one is going to be in the De Anza College Planetarium on April 23rd, and for that one, there will also be full dome immersive visuals directly from the Rubin Observatory, and our speaker is one of the postdocs at KIPAC, John Franklin Crenshaw, who will primarily talk about cosmology. So his expertise is also more in dark energy and dark matter. So and if you're interested in checking out other KIPAC events, here is our QR code. And I also got inquiries about how to sign up for the SMCAS mailing list. And Marion, do you have any final remarks to say to our audience?
Well, you also publish your KIPAC events at our SMCAS news.
Yes.
So you see,
Yes.
those members who are already on that
Mhm.
generally get your KIPAC updates.
Yes, absolutely. And I also want to mention that everyone who's here, since you already have a registration, we're also going to share this information and also the mailing list from both of our organizations with you tomorrow. So in case you want to, just check out some other events from the partners. Yeah. Any closing remarks, Marion?
No, just want to thank Theo and want to thank KIPAC and all our KIPAC guests. This has been great, and we really hope you'll keep an eye on our event calendar and come back and see us again real soon.
Come to one of our star parks.
Yeah. I think we can probably up the lights and feel free to come over. Yeah. So.